the last lecture only, we found the priority function for electrons in the donor energy state, which was now if we assume that ED minus EF is several times greater than KT, then the exponential term in the denominator will be significantly greater than 1, so that the formula can be approximated to and if ED minus EF is significantly greater than KT, then also we can say that EC minus EF will also be significantly greater than KT, which is nothing but the Boltzmann approximation. And we already know the formula of free electron concentration when the Boltzmann approximation is valid to be equal to Nc multiplied by exponential minus Ec minus Ef divided by Kt. We can now determine the relative number of electrons in the donor energy state compared with the total number of electrons. In other words, we can consider the ratio of electrons in the donor state to the total number of electrons in the conduction band plus donor state. The Fermi energy cancel out of this expression, and after rearranging the equation, we will get the final equation to be like this, in which if you observe that the factor Ec minus Ed is nothing but the ionization energy of the donor electrons. Similarly, we can also observe this data in the form of a graph. For reference, we will assume an N-type semiconductor. At very low temperature, almost all the donor energy states are filled. Nd plus represents density of electrons which are ionized. At low temperatures, very few electrons present at donor energy state absorb energy and move to the conduction band, so that the total concentration of free electrons in conduction band becomes somewhere between intrinsic carrier concentration and the doping concentration. This particular region is called partial ionization. However, as the temperature increases, more number of electrons from donor energy state absorb energy and move to the conduction band. There will be a certain temperature above which almost every electron present at donor energy state has absorbed sufficient energy to move to the conduction band, making the free electron concentration in conduction band to be nearly equal to the doping concentration. This region is generally shown as the region of complete ionization. Similarly, as the temperature rises, more and more number of electrons of the donor states come to the conduction band after getting ionized. And at very high temperatures, the extrinsic semiconductors lose their identity and begin to react more like intrinsic semiconductors. And at super low temperatures, where the concentration of ionized donor electrons is very less, this region is sometimes also called as freeze-out region. Similar analysis can be done for p-type semiconductors as well.